this video lecture, we're going to talk about measurements and their importance in engineering, and this will lead you to the first group lab activity. So what I want to do is to give you an introduction to the importance of measurements in engineering, and then tell you briefly about the fundamental and derived units that we use in engineering systems, and then end with a description of the lab activity that you will perform. So let's begin with a picture of the Mars rover and ask ourselves, why do we send robots to other planets? And obviously it is on one hand to discover things about the planet that we don't know and that we cannot do from our own planet. You might want to discover, for example, how hot or how cold the planet is. Does it have an atmosphere? Is there life on it? Was there life on it? What is it made of? And many other questions like that, right? So the point is that we want to learn and discover. If you think about it, this learning and discovery process is being linked fundamentally to our ability to make measurements on the planet. We want to be able to measure the temperature, measure what gases there are, measure for evidence for biological features, take rock samples and determine what it's made of. So it's all about making measurements. So in a sense, making measurements are critical to learning, and in order to be able to learn and to be able to make good measurements, we need to design good engineering systems, and in turn good engineering systems are actually linked to being able to make very good measurements so that we can learn. So in a sense, learning is critically linked to our ability to make measurements. Now let's look at this slide here, and I have two different engineering systems that we commonly see around us. One is the cell phone and one is the car or the automobile. So think about a cell phone. What do you think about it? What do you think about a cell phone? For example, let's say you want to replace an old cell phone, or you want to go buy a new cell phone. What are the features you're going to look at? Here are some of the things that I have put down. Of course, you'll have other features as well, but this is just a short list. You might want to think about how big the phone is, how much memory it can store in terms of photographs and videos, what is its battery life, how good is the screen, how large is the screen, how bright is the screen, how much does it cost, right? Now, what are these in terms of engineering measurements? Well, size is related to the size in centimeters, maybe the length in centimeters, maybe its weight in grams. Storage is related to something known as the memory of the phone. It could be measured in a quantity called gigabytes. The battery life is measured in time, like hours. The screen is measured in terms of its brightness, which is the units of the brightness or luminescence is candela per centimeter square, and so on. So we are ultimately making some measurements to tell us what those features of the cell phone are. Now let's look at the car. When we think about a car, what are we thinking about? How fast it can go, how far it can go, how quickly it can start from stop, how expensive is it, things like that, right? And again, these are linked to fundamental engineering quantities. For example, how fast it can go is related to its speed. How far it can go is related to the mileage, let's say in miles per gallon. How quick it can start is related to its accelerating power or its acceleration in meters per second square. And how expensive it is related to dollars. By the way, acceleration is in meter per second square, so this should be meter raised to power minus 2. Meter second raised to power minus 2 rather. So please make that correction. Okay, so the point here is that any useful engineering system has a set of measurements that represents its performance. So making those measurements are of course critical to being able to make a useful engineering system, If you want to sell a cell phone or a battery or a car, you need to be able to make the right set of measurements and do it accurately, so that you are a reputable company and are portraying the correct characteristics of the device or of the machine. Okay, so now let's look at how we get to the point of measuring such complex things in terms of the units that are involved. So we'll start with what are known as the fundamental units of measurement. We're going to use the international system of units called the SI units, and in the SI units it turns out that there are 7 fundamental units of measurement, and these are length, time, weight, temperature, current, quantity, and luminous intensity. So each of these 7 quantities, the actual measurement units is provided in parentheses here. For example, meter is the fundamental unit of length. Its symbol is M. The fundamental unit of temperature is the Kelvin. Its unit is K. Weight is kilograms and kg, and so on and so forth. So those are the fundamental units of measurement that that one would make. But in engineering, as you can analyze from what we talked about the cell phone and the car, it is not always a simple fundamental unit that is showing up in the measured or presented characteristic of an engineering system. So what that means is that in engineering, or as engineers, we also measure something known as the derived units, which are a combination of many fundamental units. So here's how it will look like. Think about the area and the volume. Right? The area now is the square of the length, and so it appears as meter square. The volume is a quantity that is the cube of the length, and so it appears as meter cube. So these are now derived units appearing from the fundamental unit of length. Similarly, we have speed, which is length divided by time, meters per second. We have acceleration, which is length divided by the square of time, or meters per second square. And then we have quantities like force, energy, and power, and so on and so forth. So the derived units are coming from a combination of the fundamental units. Okay. One of the units that does not appear either as a derived or a fundamental unit is the unit of computer information storage, that is known as the byte. And a byte contains 8 bits of information, and a bit can have, if you think about a computer, a bit is either a 0 or a 1, which is an on or an off state, and all computations in a computer are done by using binary systems, and that's why the byte is an important unit that one should know about. But it is neither a fundamental unit nor a derived unit. Rather, it's a special unit. So with that, pause the video here and try and do these 2 exercises related to fundamental and derived units. In the first one, try and figure out which of these are fundamental units. Okay, a nanometer, an astronaut's mass on the space station of 85 kilograms, the mileage of a hybrid car of 50 miles per gallon, the size of an image file on your computer of 120 kilobytes. And in the second part, try and see if you can find the dimensions of these quantities in the SI system. First one is F equals ma, where you take the mass m and you multiply it by its acceleration a. You find out what E is in terms of F times X, where F is what you just calculated in the previous step and X is a distance in meters. Similarly, try and calculate P. By the way, in an earlier lecture I said that the size of our hair is of the order of tens of microns. So a micron, which is spelled M-I-C-R-O-N, is 10 to the power minus 6 meters. Okay, so that's something to note about. Okay, so with that, let's move on to the first hands-on activity you will be doing, which is making measurements. And you will make measurements on a very interesting engineering system, which is the balloon. And the first experiment you will do is to find the relationship between the linear size of a balloon to its volume. And so what you're going to do is you're going to inflate a balloon like shown here, and you measure some linear dimension. For example, I'm going to measure the length like this to the volume of air inside the balloon. Okay? And you're going to make this measurement for different combinations of length and volume, and then try and generate a relationship that describes how the volume changes with the length of the balloon. In experiment 2, you're going to find a relationship between the time that a balloon moves once it's released after it has been inflated to its linear size and volume. So the linear size and volume is what you calculated in the first step, and you're going to use that information now and relate it to the time for which a balloon can move once you release it. So all the information that you need for this hands-on activity is provided in the lab guide that is uploaded and available for you on Canvas. For those of you who can finish off early and need additional activities to perform, you can go ahead and do some advanced activities. For example, you can try and find a way to determine or measure the thickness of the balloon wall as it expands. You can also try and find a way to determine the surface area and the perimeter of the balloon in relation to its volume. Okay, thank you very much for listening.